Alright, so let's put together what we know about interference patterns at this point to talk specifically about the double slit experiment. So basically what this is we're going to send an incident plane wave in on a single slit. And that single slit is then going to start bending light so that now it's incident on two slits. And what we're doing is we're basically making sure that since all of our light is coming from a single source here, that whatever arrives at these two slits, slits 1 and slit 2, has to be in phase. So this is just ensuring that the light coming through our two slits is in phase with each other. And so what we'll have now is we'll basically have this slit will act like a source, this slit will act like a source, and what we'll end up getting on our screen is this interference pattern. So here again is the center line sitting here that lies at the midpoint between our two slits. And then you can see that there's going to be dark fringes, which are minima, where there's no light. Those are going to correspond to path differences that are half wavelengths, so half, 1.5, 2.5, 3.5. They're going to be mirrored on both sides of the center line. And then there are going to be bright fringes that are going to be places where the path difference is even wavelengths, or whole integer numbers of wavelengths. So 1 wavelength, 2 wavelength, 3 wavelengths. And again, that pattern is also mirrored on both sides of the center line. So that this is the interference pattern that shows up on our screen from light coming through our two slits. So how do we explain this? Well, again, one of the things that's important about thinking about the double slit experiment is that what we're going to end up doing is it's going to be like the interference problems that we've worked so far, with the one exception that we're going to be able to make the assumption that the light from our two sources is effectively going away from the slits parallel to each other to reach this point on the screen P. So when we can make this assumption, that means that we've got a triangle here that's going to be related to the path difference that we can use. So you'll notice that if these two rays are going away parallel to each other, then basically this point right here, right, this is how far both waves travel, plus the wave from my second slit has to travel this additional distance. So this distance right here happens to be my path difference. Well, this is a right triangle. This is the angle theta. Theta, again, is where are you relative to the center line when talking about point P. So if here's the center line of my pattern, this angle up here is theta that gets me to the point P that I'm interested in the interference. That angle theta is also going to be the angle theta sitting in here. And so when I look at this, I say, okay, that means that the sine of theta has got to be the opposite side, path difference, over the hypotenuse, which is the distance of separation between my two slits. I can solve this and say, well, what this tells me then is that the path difference has got to be equal to d sine theta. So for whatever point P you're talking about, the path difference, what's going on at that point, has got to be equal to d sine theta. The other triangle that is going to be relevant here is, again, there's going to be some distance from my slits to screen, and usually L is going to be much larger than D. So here we're sort of zoomed in to see what's going on at the slits. L here is the distance from slits to screen, and then Y is the distance from the center line of my pattern to the point P that I'm interested in talking about what's going on in the pattern. And again here, same angle theta. The tangent of that angle, opposite side over adjacent side, is going to be our distance y over L. So I've got sort of two equations that I'm going to use. One's going to tell me about sort of what the path difference is and therefore what angle I'm looking at. The other is going to relate that angle to where I end up looking at a point on the screen. So here's the equation that sort of defines what the path difference is at the particular point P in my pattern. And so if that point happens to be a maximum, then I've got constructive interference, which means that I can also talk about this path difference being equal to 0 or 1 lambda or 2 lambda or 3 lambda or any whole integer value of lambda. So equating those two things, what I get is that d sine theta, this way of talking about my path difference, has got to be equal to m times lambda, where m can be 0, 1, 2, 3, any whole number. 0 corresponds to the central bright maximum, and then 1, 2, 3, those are all my bright fringes. So you'll notice that this actually works out quite nicely, that when we want to talk about the first bright fringe, we're going to use 1. The second bright fringe gets 2. The third bright fringe gets 3. The second option I've got, or at least the second sort of specific point I might be interested in, is if the point I'm interested in happens to be a minima. So those are cases where those points correspond to destructive interference, which means that my path difference has got to be equal to these half wavelength values. So half a wavelength, 1.5 wavelengths, 2.5 wavelengths on up. And so equating these two things again, I get that, well, d sine theta is equal to, and we're going to use n for our minima. And if we do n minus 1/2 times lambda, then again, n can still be 1, 2, 3. And so the first dark fringe is going to be n equals 1. The second dark fringe is going to be n equals 2. The third dark fringe is going to be n equals 3. So using this equation with the minus basically enables us to talk about the dark fringes, use the same number to describe the dark fringe is what we're actually going to plug into our equation. And so I can deal with situations where I have a problem where I'm told what the angle is, and so therefore I can figure out what the path difference is, and then go ahead and think about maybe what the phase difference is. Or I can have problems where I'm given particular types of interference, so either maxima or minima, and then use those points to again figure out what's going on, say either with separation between my slits or the location using my tan theta equals y over L, the location of things on the screen. So those are fundamentally how we're going to end up working with our double slit interference problems.